Okay, let's go to our notes. Okay. Okay, last time we did this. Okay, the how to reverse, right? How to reverse the order, how to change the order from dy dx to dx dy, or this one is taking on some specific function that you need to integrate, and then you are given the informations, and from these informations what we can do is we can set up our integrals, and this is what we did. Okay, and then if we have this question here, uh, if we are going to directly look at the integrations, if we try to do some techniques, and if you can find one, then probably you need to change the order, right? Change the order from dy dx to dx dy, or vice versa. Okay. Okay, I will continue a little bit more on this double integral, and after that, maybe giving you two practice, maybe two questions, and then we move on to 15.3. Okay. Okay, let me write in the new note, new page here. Let me go through, okay, maybe here. Okay, if I have that z is equal 1, okay, so the surface is just a plane, okay, just a plane, then we can write down uh, that, so let the function is equal z, and the z is equal 1. Okay. So the function is just a constant. So if we have this, okay, if we want to write in multiple integrals setup, so we can write double integrals, okay, and this is the boundary, the area, right? And the inside is just a constant, right? Because z is equal 1, or function is equal 1. So you just write dA. So what's the implication of this these equations? The implication is if we are going to evaluate this will be equal to the area, right? This will be equal to the area of D. Okay. So if we look here, if you try to find, then it will be 1, right? The height is 1. If we look here, the height, right? This is the height, and this is the area. Then the volume is equal to the area. Okay. I hope this clearly can be understand. So we can write the AD multiplied by 1 AD. So this is volume, right? So you can also try to evaluate and making the functions as a constant if you want to evaluate the area, and you can just take the double integral and take dA. dA can be dx dy or dy dx. Okay. Okay. Now the next thing is, if we would like to have a setup, okay, based on this statement here, if you want to set up, if we have a constant m, a small m, we have a setup that is the function is between the small m and the big M. We have two constants. So if this happens for all points in D, right? And then if we try to multiply, let me write multiply with AD. Multiply with AD and multiply with AD. Okay. This is precisely, we can write that this M AD, this is the height, right? This is the area. So area height, if the height is just a constant, okay, then this is precisely we can write as a double integral x, y, dA, and then let's equal capital M AD. Okay, so what's really happening here, and how do we apply or implement this inequality? So if we have picture here, this is saying that our function is in the between this M, right? Functions. Okay. Okay. So if we, for example, we have E sine x cos y and then dA. If you would like to look at this double integral, and we would like to observe and analyze using the inequality. So first, we can start with the trigonometric sign, which is we have this inequality and also cosine. So if we combine these two, still we have possibility for -1 sine x cosine y, right? This is true, right? Because sine and cosine, the possibility is just -1 and then 1, right? And because of the function of e is increasing, function of natural exponent is increasing, then we can write down that e and e also e. This will be in our calculations. Okay, if we look at the integration, okay, if we have another, it gives us another information. Okay, D is region. I forgot to write this. D is region with with what with? It's a region. The disk, okay, with center 0, 0, and radius is equal to, so it's a circle with the radius is 2. Okay, so which means that if you would like to calculate the area, this should be pi r squared or pi or 4 pi. Okay, if we try to multiply all this with a, which means we are going to multiply with 4 pi, this will be 4 pi over e. This would be this, right? You can write in these terms also, and this will be 4 pi e. So we could imagine, we could visualize the double integrals in a inequality form, and we can observe that the value will be in between some of the constants. This is 4 pi over e and up until 4 pi e. Okay. Usually this is quite helpful if you are going to implement in some estimation. Okay, if you want to estimate some values for and you can measure using double integral, then you can measure some how minimum the value is and how maximum the value is. Okay, so it's similar to what we have in max and mean value for double integral. Like in partial derivative, we have maximum minimum value for a function. now this is maximum and minimum value for evaluating the integral. Okay. Or we could say evaluating the volume with the height constant. With the height constant. Okay, I think I can go for some example. Okay, let me go through. Okay, I think I can give you some examples. Okay, so let me wait for a couple of minutes for you if you want to take notes. Okay, let me give you two questions about this one. Okay, so let me go through the next page. I give you example. Find the volume of given solid. First is uh, enclosed by planes z equal x, y equal x, x plus y equal 2, and z equals 0. And the second is enclosed by cylinders, y squared plus z squared equal 4, plane x equal 2y, x equals 0, z equals 0 in the first octant. Octant means like quadrant. If you remember, quadrant has 4, octant has 8. Okay, so first octant is the one that has all positive. Okay, the axis is a positive axis. Okay, try these two questions. Maybe try the first one, the number A. If you finish the calculations, you can write the answer in the chat box. Okay. Number 8. Is anyone ready to get the answer? First is you need to recognize which one is your functions. Function of two variables and which one is just the area projections at the xy plane. Okay, anyone has the answer for the first one? Are you still not sure how? Okay, Palace. Yeah, slowly. It's okay, slowly. Okay, we'll wait for a couple, maybe one or 2 minutes, and we can solve together. Okay. I hope you are trying your best to at least. Um, First thing you need to do is imagine the graph, right? So drawing or sketching the curves, at least the area, the area part is, uh, I think, essential parts in double integral. So you don't you don't really need to draw like the 3 dimensions part, but the projections, that is the one that we are focusing. Okay, I think I will help you to sort out this problem. Okay, so first we look on these problems here. We have this. We are going to look at that the z. Okay, z is from x to, or from 0 to x, from 0 to some x. Okay, and y equal x, and this means that we can treat this in terms of y or x. So if we treat with the y, then we will have x, and then 2, and then sorry, maybe y, and then x, and then 2 minus x. Or I think we can just directly, for x and y, we can just draw in our xy axis. If you want to just avoid any mistake that we might have for some assumption. So we could just draw the x and y. So we could draw first is the y equal x, and draw the x plus y equal 2. So x plus y equal 2 will be let me go maybe around here. This will be 2, and this will be 2, right? So I will connect these 2 points. Okay, I think that will be very clear. And this will be x plus y equal 2. Okay, and if this is 0, so we could start with the what kind of area that we are going to have. So we would have, if you try to equaling both sides of this y equal x, and y equal 2 minus x, we could have x is 2 minus x, that x is 1, y is also 1, so this will be 1, 1. Okay. So this will be 1, this will be 1. So we could try to look at which one that we are going to take on. Okay. But before that, to just remind you that we have z from 0 to x. So we will have something in, if we have the 3 dimensions, if you can imagine, z will have something uh, something similar to what we have here, y equal x, but it's on z with, it is on z and x, right? So we have z equals 0 and then z equal x at the upper side, or we could let the, if you just let the z is a function of xy, then we could say that the double integral, this is d, then it is z, or now it's because z is equal x, so it's x dA. This is the first step that we can write. Okay. The next step that we can write is we can take our x and y and take it into dx dy or dy dx. It's depend, because I think both x or y should be fine. It doesn't need to be like both are, I think, doable, and you can calculate both dy dx or dx dy. So if we take, for example, if we take the x as a constant, so we take this as a constant, so 0, 1, so we should have the outside integral. Let me write. Let's say if we would like to have dy dx. So we would have dx from 0 to 1, so we should write the outside integral as a constant, right? And the inside integral, it should be y. So y should be start from here, which is we have y equal x. Okay, so we start from x to this line here, which is we have 2 minus x, right? So we should have from x and then 2 minus x. Oh, sorry. That will be our double integration. Now, why I'm choosing dy dx? Because we have x, right? And if you integrate x, we just adding y, right? I think that will be better choice for calculation. If we try to take on dx and then dy, we will have this in terms of x. If we want to integrate, this will be x squared over 2. And if you would like to put in the equations, this will be equation of y, right? Rather than x, this will be y. Then this will be resulting in some calculation with square. And I think I didn't want to calculate in a complex way. So my suggestion is try to be efficient as you can. Okay? So that's why I'm choosing this dy dx. Okay, let's continue here. Now from this part, let me go here. Okay. From this part, we can, this is x, y, from x to minus x, and then still we have dx. And then we put on x, 2 minus x, and then minus x squared. And it's still 0, 1 dx, right? So we have 2x minus, maybe going here. So 2x minus 2x squared, right? So we will have 2, and then this will be x squared over 2 minus x cubed over 3 from 0 to 1. So 2 half minus of 1 over 3. This will be 1 over 6. So this will be 1 over 3. That will be the answer. Alternative answer, if you stick to dx dy, y will be taking on 0, 2, and x will be from it has two sections there. Okay, I think we should have x equals 0, and you could have two sections here, so we could have another plus. Yeah, it's a little bit complicated to write because we have one sections is the x equals 0. The other one will be this 2, right? This 2. So I'm not suggesting dx dy. Okay. Okay. The second one, anyone trying to solve? Okay, let me keep you slightly. It has a cylinders, this one, and it has a plane x equal to y. So it should be go through probably here. This is, I think, this is x equal to y. And then x equals 0 and z equals 0. Okay, now if we imagine that if this is x equals 0, right? And I believe we need to imagine the cylinders. Okay, so if this is y, this is x. The y squared plus z squared, this will be going to have, let me give you some perspective. So if this is z x, sorry, maybe y x to make it easier to look at. This will be the cylinders, right? The cylinders. Okay. Okay. So the first octant will be if we have complete. The first octant it should be goes about this one. Okay, the one that is all positive. Yeah, I think still difficult to see. Okay. Okay. Now when it's z is zero, we could take the intersections to our cylinders. Okay. We could take that y squared should be equal to 4. So y will be plus minus 2. In the first octant, we should take all positive, right? So we just need to take on the positive 2. Okay. So positive 2 may be around, maybe here. This is 2. So I will take the line. Maybe make it a little bit longer. Okay, that's y equal 2. So if we would like to take the region, which part the area that is the first octant, this will be the area. Okay. So, okay. And then from here, we could write our integrations d, and what is our function? So our function we could write from this one. So this we could write y as 4 minus uh or what z, so sorry should be z equal 4 minus y squared. Okay. And we could take the square root that is positive because we want to have the first octant. Okay, so the first octant. So take let z equal 4 minus y squared because it's on the first octant. So we need to take all in a positive value. Okay, now we take this as square root 4 minus y squared. Let's say dA. We'll write dA at the beginning. And then we need to choose dx dy or dy dx. Since we have y inside, right? What I want to do is we could have dx dy. Okay. Because if you have dy dx, it will be difficult to be integrated, right? So we could start with dx dy. So start with integrations. Dy will be 0, 2, 0, 2. And then let me write 4 minus y squared dx dy. And then x will be from x equals 0, this one, to, if we take this, so it's going to be crossing this x equal to 1. So this will be from 0 to 1. Okay. And we could take this, take 0, 2, and take x square root 4 minus y squared, 0 to y, and then dy. So take inside 2y, and we can solve this through substitution. So substitutions 4 minus y squared, du is negative 2y dy. So we could have square root of u du negative, right? So we integrate this, and this should be, let me write directly, u with power of half will be 3 over 2, so 4 minus y squared, 3 over 2, and then minus 2 over 3, right? So this will be 0 to 2. Input 2, we will have 0, right? We will have 0, and then minus should be, right? Should be plus. 0 will be 4, 8, 16 over 3, minus 16 over 3, and it become a plus. So it's 16 over 3, the answer. Okay. Okay, any questions? Any questions? Okay. To solve this, the idea is first to sketch, visualize the area, visualize the D. Secondly, to choose which integrations order you would like to have, dx dy or dy dx. That should be the case. Okay, any questions? If no, maybe giving you one more example. Or maybe I think it's enough. I think we can move on to next section, 15.3. Later, if we have more exercise, I will just compile into one video, maybe 3 questions, and then add it to the Moodle later. Okay. Okay, if there's no questions, then let me continue. Okay. So we start the new page. So 15.3, we have double integral in polar. Let me check. Okay. Okay, in polar, as you remember in chapter 10, right? Recall all the how to convert the Cartesians to polar or from polar to Cartesian. So we would have this conversions, and this will be very essential in polar. Okay. So now the question is if we are able to convert the polar from xy to r theta, can we also convert the double integral like we did before into polar, and what kind of formula that we have in polar? Okay. So let me just give you some slight difference on the polar. So if we see the left and right, we have two a polar shape, right? The left one is just a circle with a radius 1. Okay. So we could say that this is a circle with radius 1. Okay? And also in polar, we could write this just r equal 1, right? The polar curve is r equal 1 in polar. And we could draw r equal 1 like a circle. Okay, if you remember the polar. Okay. And we could have written all this x, y, and this x squared plus y squared equal 1. We could write in terms of this r. Okay, the r can be written in r theta, 0, r, 1, and then from 0 to 2 pi for the angle. And similarly, if you look on the right side, the r will be from the r will be from 1, so this is 1, right, and 2. Okay, we could say that the full circle minus the small circle, right, but it's a half. Okay, and so which means that the angle is just up until pi, not the full circle 2 pi, right? Okay, now from this element, then we could write and imagine, okay, that the region in the polar we could have. So there's two elements. First is the radius, and the second is the angle. So r and theta. That is the first thing. Now, second thing is, how do we approach the area in the polar? If you remember, we could have the sector, right? The sector. If you remember, that is the sector, right? So the sector is this area, right? And now let's write let's draw first, okay, what we could have. What we could have maybe make it a little bit bigger. Okay, now if we, let's say we have this, okay, this is our illustrations on what kind of r we could have in a polar. Okay, so we have this polar. Okay, this is theta alpha, theta beta, radius a, radius b, and it's the middle part will be our r. Now if we cut this, okay, according to the polar slicing. Polar slicings mean we have a circle. Okay, this is the origin. Then this is the polar axis. The polar slicing means that we slice in terms of all possibility for the angles and all the possibility for the radius. Okay, this is the polar pattern. Okay, it's like a Spider-Man, right? Okay, now back to here. If we slice like this one, okay, and we can imagine small pieces, right? And like in the terms of, so in all integrations, if you want to construct the thinking in integration, we could start with something very small. Okay? We could start something very small. And let's say we are taking the middle of this subrectangle. So this is the middle part. That is this Ri with asterisk and theta j with asterisk. This is we call the sample points. Okay. Now, if we would like to write the region of ij, which is this small rectangle, we could write that similarly. We say r theta, and we could write all the terms. Like for example, if we take this ri and ri minus 1 as our radius, we could write Ri minus 1 up until Ri, and theta also from theta j minus 1 and theta j. Just to show you that this is the sub-rectangle that is a small pieces when we slicing all the polar patterns. Okay. Okay. Now this coordinates. Okay. We could define this in terms of that the Ri, the middle part, is the average. Okay, the average value of our Ri minus 1 plus Ri. Let's say this is our definition. And the theta will be also the average value of theta j minus 1 plus theta j. Let's say we have these two average value as our definitions for the center of the rectangle. Okay, now if we could take the area of this rectangle, okay, so we could write the delta A, okay, for that small rectangle. We could say that because we remember that we are going to take this as our approach for the area in the circle, then we can take this part as half Ri squared delta theta, okay, and then minus half Ri minus 1, and then squared delta theta, okay, and then this is equal to half Ri squared minus Ri minus 1 squared, and then delta theta. And we could factorize and then base with our definition here, we could write this as Ri asterisk delta R and the delta theta. Okay, now from this equation, this is just the delta A, or we could say the delta AI, because it's the small one and not the total area. So if we are going to look at our double integral df xy and then dA, okay, what we could do now, we are going to convert the functions into our polar. So we can change the x and y with r cos theta and r sin theta. So we could write a Riemann sum. So we could write a Riemann sum for this double integral as the double sum f, and then we start from Ri. We are focusing to observe the small rectangle, so we need to write all with the asterisk term to let them be a small pieces. And then this will be equal to the delta AI, and this is the equations. So we can write delta R, delta theta. Okay. Okay, we can continue. Or if you want to take notes, you can take notes first. Okay. Now we could write, we take this a little bit to the left here. Okay, if we have function g, here we have functions g. If g is a function of polar, then we could write the g as f. So we could take this into the integrations of alpha, beta, a, b, this is g, r theta, dr, d theta. Okay. So if this okay, let's continue. I hope you finish this notes for this one. Okay, let me move to this one. Okay. So in conclusions, if we have the double integral, if you want to convert, okay, to the polar, let me write the definitions in terms of limit as the m and n going large. Let's say delta a I. This is certainly the same as limit g and then delta r delta theta, or we could say that this is integrations from alpha to beta. This is g r theta dr d theta. Okay, and this certainly equal to, we turn back to the f, that this is the alpha beta a b f r cross sine theta r sine theta, and then don't forget r dr d theta. Let's say this is r, to make it same terms all over the place. So this will be the convergence. Okay. So what this formula means. So if we want to convert from the double integral, from the left one, if you want to convert, then we convert x, it could be r cos theta, y will be r sine theta. And the important thing is, don't forget this r. You need to do multiply r. We have another proof later, and I think at the end of the section 15.8 or 9, that this should have been r. Okay, and we can have proven later on. And also, I think if you are going to take some logic, if you draw, sorry, not this one. If you draw from a small sectors, okay. If we try to take the small polar sector like this one, if we remember, this r theta is our arc length, right? Like in the circle, we know that this is our angle, right? We want to know the length of this, right? The length is precisely r theta, okay? So if we have d theta as our angle here, then the arc length will be r d theta, okay? Now, what's happened to dA is, if we imagine this as a rectangle, then we could, or we are multiplying dr with r d theta, which means that this is practically similar to what we have in the formula here. Okay, so if you maybe feel that the explanations from this sections maybe too much formulations, too much words, I think you can just take small part of the polar sector, and then you can imagine, and then trying to construct the dA. Okay. And it should be written within the order r dr d theta. Okay. Okay. Okay, let me give you some example. So this is the important part, the one that I'm making box. That's the one that I think important. Okay, now if we have a questions, for example, double integral -1, 1, and then 0, and then 1 minus x squared. This is x squared plus y squared, and this is dy dx. Okay, it seems it's doable. It seems. Okay, for example, we start with dy. We could write down the formulations to be x squared y, and then y cubed 3, right? But then we need to input this y minus x squared in the square root. So I think it will be, at least it seems very complicated if you would like to force out our way through this one. Although not sure on your calculators whether you can do some double integrals or not, but I think in sense of our calculations by hand, this is not doable, right? not doable. So what I could have suggest to you is if we could let this x squared plus y squared into a polar. Okay, so this is a circle, right? This is a circle, so we could write this as r squared. Okay, and then we could see that x is from -1, so we could write -1 x 1, and then y will be having from 0 to square root of 1 minus x squared. And we can actually see that if we want to look on these sides here, it clearly say that we can write equations in terms of y, and we could write this in terms of a circle with radius 1. So we are dealing with a circle, or to be precise, it's a half circle because we start from 0. Right? So we could write down or draw, or let me just give you the drawing. If I have the drawing here, I think this one. So we could start to draw, and looking at the axis start from -1 to 1, and the y start from y equals 0 to the circle, the half circle, right? So we could say that we could write the r. Let me write completely. Okay, you can skip this in your exam and just focus on finding the answer. But let me just write this for you. We can convert this to r theta, which r is, the radius is just 1, right? So radius is 0 to 1, and the angle is from 0 to pi. So 0, so this is 0, right? Theta is 0, and then this is theta is pi. Okay, and then we could write the new formulations for the double integral. It's become, or let me write completely, from -1 to 1, 0 square root of 1 minus x squared. This is x squared plus y squared dy dx. So we could write first is 0 pi, the second is 0 1, and then x squared plus y squared is r squared. Dy dx become r dr d theta, and this will become r cubed. Okay, so r cubed integrated, that will be r4 4 0 1 still 0 pi theta. So we will have 1 over 4 or pi over 4 at the end. So whenever you have a functions in the double integration and you think that you can convert into polar, and you can maybe dealing with the questions easier, then perhaps you can just convert to polar and just evaluate. Okay, any questions? If you have any questions, you can just write down the question. Okay, let me give you some time to take notes. Okay, I think we can take another example to give you more insights on this polar polar coordinates, double integral and polar. Okay, next question. Example, find the volume of solid bounded by plane z equals 0 and paraboloid z 1 minus x squared minus y squared. Okay, let me give you a couple minutes to try. Okay, so the plane z equals 0 will be at the xy plane, right? Projection, the plane z equals 0. And the paraboloid z equals 1 minus x squared minus y squared. If you look on, just take a look, if we take the 0, then we have a circle that is precisely x squared plus y squared equal 1. This is a circle. So we could see that the paraboloid is above this circle. Okay. So we could write down, or we could draw, if you would like. It's easy to draw this, but the important thing is to take notes that we have the circle. We have the circle that is, we draw a circle maybe here, that's circle. So this circle will be our observation. So from what we have seen here, if we are likely to write the double integrations as it is, like for example dA, we could write this. For example, if you take -1 and 1, and this part will be x squared, or 1 minus x squared, and this part will be -1 minus x squared, okay, this part here. So we could write this also in -1, 1, -1 minus x squared, and then 1 minus x squared, and then this will be 1 minus x squared minus y squared dy dx. This could happen. But then if you take times to force your way out and then plug in this 2 square root, will be very, very difficult, right? So the only plausible way that's doable for you to write is, let me write, and we could see from the circle, it's just a full circle, 0 to 2 pi, and it just have radius from 0 to 1. There is no other sections, right? And we could write these terms here. It's 1 minus r squared, okay? So 1 minus r squared. Don't forget r, and then dr d theta. I think it's now becomes more humanly possible, right? Humanly possible. Okay. So let's just take this r minus r cubed. So we would have r squared over 2 minus r 4 over 4. And then this will be from 0 to 1. And d theta, so 2 pi multiply with half minus 1 over 4. So we have pi over 2. Okay. Okay. So the examples we did from this example and then the previous example, we are all doing the constants, right? If we look on the polars, we see a constant, right? Constant, constant, constant. And this one is also having a constant. So what's happened if we are observe not a constant, but rather a polar curves. Okay. So what polar curves means? It means that in our sections today, or this polar, we would have, or we would encounter chapter 10 problems, the polar curves. Okay, so if you remember, we have the cardioid, we have the rows, the lemmason, and so on and so forth. That polar curves can also be our problem in the double integral. So we will have a more general equations for the polar equation. So let's take on this picture and giving you a context. Okay, so what the polar curves mean is you could have the radius in a function of theta. Okay, the radius is function of theta. So let me write if functions continues on polar region and d is r theta and the r is function of theta h, then we could write the double integral. This will equal alpha beta and then h1 theta, h2 theta, and then this will be f r cosine theta, r sine theta, r dr d theta. So it should be written as it is. So r dr d theta is always written in order. Okay. Okay, any questions before I move to the next page? I believe this is quite important, but I think you don't really need like take notes for everything. What I need to emphasize in this case is uh, it's actually still similar. We are using the r right here, but now r can be defined or described as a function of theta. Okay. Okay, I will go to the next page. Do you have any question? No? By the way, like I mentioned in the beginning of the class, since we will have online exam, So I think your exam should be, I will just say, open book. Okay, so you can review your notes. You can open your notes, and also you can use calculators. Um, yeah, that will be the exam. So then I would like to try the questions to be a little bit more advanced because I will give you freedom to uh, to open your notes and using calculators. Okay. But yeah, the downside, the question will be uh, a little bit advanced. But I think you still can do it. You still can do it, and I hope you can do it. Um, I will incorporate, I think, the same platform that. Yeah, don't worry, Palace. It should be doable in your case. It should be doable within the time limit, right? Uh, and I will try to use uh, the same platform that you tried before in the chapter 11 quiz. I will try that platform with time limit. So for short questions, like just take the true false statement, maybe just 20-30 seconds, and for multiple choice and short questions, maybe 3 minutes, 5 minutes. But for longer sessions that you need to observe one by one, maybe taking 15 minutes, and maybe I will divide the final exam become different parts, and you need to click all those parts and finish all the exam within the time limit. And maybe for one part, you need to also provide one paper calculations just to show me that you are uh, you are writing all the necessary steps solutions. But I think for the other parts that just multiple choice, then you just try uh, to take the answer. If the answer is wrong, then um, probably just a 0 point for that question. So there will be a different at least 2 or 3 different parts of the exam. That's one way to deal with. Yeah, because I I tried I think last year doing online exam. Also similar case with today. With today's case, we are having online classes until the end of the semester last year, and we are also doing the online exam. But unfortunately, because I'm not really prepared for the online exam, there are some few part that is not prepared for, like for example, uh, the supervisor cannot be control all the students all the time, so uh, that will be uh, the case, and I'm not sure all the students will, like, for example, if you are in the same room with your friends, you could have discussions right now. I wouldn't know, and that will happen. So if I make it like each question has time limit, and they need to click on the link and uh, write down the questions, um, then should be it should be helping me to at least uh, restrict the students. Although if you are trying to find a way, there is always a way if you want to go for a negative way like cheating. But I don't think it will be helping you. Yeah, it will help you maybe pass the course, but it will not help you in the future. Yeah, I promise that. So yeah, later I will discuss more about uh, how we could proceed with exam in the future. Okay. But for quiz, uh, I think this afternoon I will upload the link to you. I think I will just open for 5 days, so you can pick up your free day, maybe weekends if you have time on weekends, or any day you can try. Okay, that's the, I think, announcement for how do we proceed in the future exams. Okay, let's continue. Okay, let's giving you a example on the polar. Okay, example: find area enclosed by one loop of rose curve R cosine 2 theta. Okay. Okay, I hope you still remember cosine 2 theta and how to draw them. If you are maybe not familiar, you can start by scratch, but I don't think start from scratch can help you. Maybe start from, imagine the polar, okay, the polar curves. So polar, we start by taking that this is theta equals 0 and this is theta equal pi over 2. It's not y or x. Okay? It's not y-axis, it's not x-axis. It's different. Okay. So what we can do from polar, we can start, remember that the polars always start from theta equals 0, and it goes by as theta getting increase, it goes through here. Okay. And then we are going to look on the radius. So if we look on this r equal cosine 2 theta, we have the maximum radius is 1, right? When cos is 0 or 2 pi and etc. So we could say that we start from this 1, okay? And if you want, you could try some angle that is special, and you could imagine how it looks like. And then when theta is pi over 2, it will go back to the 0, go here, right? And if you're doing all the radius, and you need to keep in mind that if you get, because sometimes cosine getting negative, right? But how we can draw the negatives in the polars? The negative can be drawn, r negative can be drawn as if it is the opposite side. So for example, you get -1, then it should go behind. So maybe it should go over here. Then you need to draw here. Okay, you need to go to the opposite side. And you can, I think you can try to watch some tutorial on YouTube on how to make the polar if you forget. Okay, but let me give you just a shortcut for the rose curve. Okay. So if we continue drawing the rose curve, we would get this 4 leaf. Okay, we would get this 4 leaf. And if we have the cosine pi over 2, means that the theta will be pi over 4 and negative pi over 4. This should be, so this will be theta pi over 4. Okay, just to remind you. Okay, now one loop means it can be this loop, it can be this loop, but let's just say we just focus on the first loop here. It should be the same symmetry, right? It's the same area. So we could write down that from here we get the notions that the theta is from negative pi over 4, so we could write negative pi over 4, pi over 4. Okay. And then we could start to write what kind of radius we have here. So the radius is, we can have radius 0, right? We can have cosine is 0. So we could start cosine 0. And then we could have the cosine 2 theta as our curves are. Because it's the radius is getting vary, right? It has some variation of numbers. So that's why we have the polar here. And then what we have is just r, dr, with theta. So this is, I believe, also similar to what we have in the previous one when we say that the d, and then this, if we just one constant, this is, we say, we could say that this is alpha, beta, and let's say this is 0 to some function of theta, r, dr, d theta. Okay. Now, if we try to solve this, okay, if we try to solve this, this is just to remind you what we have in chapter 10, actually. So alpha, beta, and we solve this, integrate, become r squared over 2, and take in h theta, so d theta. So we could have alpha, beta, half, okay, half, and then h theta squared d theta. This will be the integration formula in chapter 10, right? This is the r, right? The r squared. Okay. So this is the AD, the area of this. Okay. So which means that this is the area of the integrations in the single integral and polar. Okay, we go back to our questions here. So what could have been in our solution here? So we could write, and then we could solve the r first. So we could write this is r squared over 2 from 0 to cos 2 theta, and then d theta. So we could have cos squared 2 theta over 2 and d theta. With some double angle formula, we could solve this for cos for theta. So we could have cos for theta over 4, right? Plus 1, sorry. And maybe it takes 1 over 4 outside there. We could have cosine become sine. So sine for theta over 4 and plus theta. And then input negative 4 over pi over 4 and pi over 4. And if you input, you will get, if you type in a calculator, I think you can directly get this as pi over 8. Okay, this is just to slightly remind you in the chapter 10, but now we can also describe in double integral. Okay. So let me give you, I think, 1 or 2 questions more, and I would like to have a feedback session at the end of the class. So let me give you another questions here. Example. Find volume of solid lies under paraboloid z equal x squared plus y squared above xy plane inside It's a little bit complicated now. Cylinder x squared plus y squared equal to x. Okay. So how to start? Okay. How to start? Okay. To start, okay. I believe paraboloid can be imagined. Okay. You have x squared and y squared parabola. You combine and becomes paraboloid with the center axis is z. Okay. So you have a circular paraboloid. Okay. And then the cylinder, what you could do with the cylinder is you can simplify the cylinders. Okay. You could try to grouping the cylinders and see what equation that you might have from here. So I think we can just take this plus 1, right? So plus 1. So we could have x minus 1 squared plus y squared equal 1, which means the cylinder has a center 1, 0 at the center, right? Okay, at least from here, you could easily imagine like you have a cylinder and you have some intersection with the parabola, with the paraboloid. Okay. I think I have the picture. Let me give you the picture to give you or to let you imagine. Do I have the picture? Oh, I don't have. What's this? Oh, no. Let me just give you a picture, a quick look on how we could draw this. So we are having the I think I will just draw with hand. So we will have the paraboloid, okay? And we have in 1, 0, let's say this is y, x, z. Okay, at the 1, 0, 1, 0 should be here. Okay, this is the circle. I think a little bit bigger. So this will be going to have a cylinder. Yeah, it's really bad, my drawing, sorry. At least you can see that it is going to cut here. Cut the paraboloid here. Let me just draw with different color. So it's cutting here. Okay, if you see, it's projected through to the circle. Okay, and
okay, I found this on the web for who is projected to add to the circle. Check it out.
Okay, now we could write the r theta as, okay. So we have the projections is this circle. This circle. Okay, we could have this circle. If you remember what kind of polar we have here, if we try to solve, maybe let me give you slightly equations to make you remember. So this we can write as r squared equal to r cos theta, or r is to cos theta. Okay, so this is a cos theta polar, right? Cos theta. But to be precise, we have 2 cosine theta, okay, from our 2 cosine theta here. Okay. Now we have, this is pi over 2, right, for cos theta, and this will be negative pi over 2. Okay. So we would have, this is negative pi over 2 until pi over 2. And then r is start from 0 to cosine theta. And we could write down the formulations as negative pi over 2, pi over 2 from 0 to cosine theta. So r squared, this is the z, okay, and then r, the r, the theta. So you could say, we could solve this first, becomes r cubed, and then integrations become r4 over 4, and then plug in 0 and cosine, 2 cosine theta. I think it's still doable, although you could see that we have cosine with 4, with power of 4. What we can do here is, we can imagine this cosine as cos squared theta squared. Okay, and what we can do is, we take this to the double angle formula, make it this, and then square. Okay, and then expand the formula. Okay, expand the formula, and then I think you can do another double angle formula for the squared, and eventually you will get the results. Okay, I think you can do this by your own, and you should try and review your calculus, especially the trigonometry calculus. Okay. Okay, any questions? How the boundary determine? Okay, the boundary. So, as you may know from our polar coordinates in chapter 10, we start from, this is we could say we start from theta equals 0, and then we move on through the so actually, if you are confused on the drawing, you could say that cos theta so cos theta can be defined in two terms when it is a 0. So we could have a pi over 2, or negative pi over 2, or even 2 pi. Okay, but in our case here, since we are having the cross section here, so the theta, we are using the negative pi over 2 until pi over 2, because in the quadrant 4, the cosine negative pi over 2 is also 0. Pi over 2 also 0. And in the quadrant 4, both are 2 cos theta. 2 cos theta is from here. So we could change the x squared plus y squared become r squared, and then x become r cos theta, and we could simplify it, becomes the cos theta. Now why we can do this, because we are in the polar, and in the polar r is always positive. In the visuals is always positive in our visuals. It can be negative, but when we draw, it should be a positive. Okay? So we could cancel this with this, and r becomes 3 cosine theta. Okay. Oh, I think this should be positive and this should be negative, right? Yeah, same way. Okay. Any questions? I think later on you could say that you could just take device and then make it 0 pi over 2. That's also fine because of the symmetry. I think it's much more easy to visualize. Okay, sorry, a little bit messy on the last page here. But any questions? If not, let's do some feedback questions, feedback sessions. So let me go through the website. If you haven't scanned the QR code, you can scan now. But I think let's start uh, the sessions first. Wait a minute. Is this the one that we are having? Oh, no, 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 not this one. Sorry. Uh, okay, I think this one. Okay, let's join the feedback sessions. Uh, not to pi for a circle. Oh, you mean the last one, Efando? Um, actually, you can see from actually it will be the same. I think it will be the same. But let me check later. Okay, Efando. Yeah, thanks for reminding. But whenever you have a symmetry, you could take into half and make make it multiply by 2 later on. I think the easiest way to explain for that part, Efando, uh, you could imagine starting from 0 to pi over 2 and then multiply by 2. I think that's still okay. I think 0 to 2 pi also, I think also the same. Also the same meaning. Okay. But I think not 2 pi, but should be pi, right? Should be pi. Okay. You need to make sure the point, because it's 2 cosine theta, right? 2 cosine theta. So it should be 0 to pi over 2 and then multiply by 2. Okay, I think we can start now the session. So start. Okay, I hope the time is okay. I haven't checked all. Okay, are you ready? I hope you guys using your student ID at least. Okay, so we start. 3, 2, 1, start now. Okay, just a 20 seconds. Okay, should be true. It's, remember the saddle point should be that D will be negative, right? Okay. 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 Number 2. Okay. This should be a Lagrange method. So I hope you are watching my additional video on Lagrange. So firstly, you need to determine the gradient factor of the function f, and let the constraint become a function g, right? And take the gradient factor of g, and take the equations gradient factor f equal some scalar multiplied with gradient factor g, and we can have several equations. It could be linear equations that you need to solve, or you can substitute some value, and by the end of the day you will get some possibility for critical points. Okay? And from those critical points you need to determine which are having the minimum one, which means that the minimum values is when you plug in the points, which one that gives you the minimum values, or even what is the minimum value. That's the question. Okay, less than 7, 6, 5. Oh, okay. Speed negative 9. Okay, I think we could do some review on Lagrange method later on. Okay, next one. Yeah, I hope you don't mind. It's giving you a different variable, but it's still the same. It's just like dy dx dx dy. Okay, sine cube. We can solve sine cube with you can have sine and sine squared, and sine squared can be 1 minus cosine squared if you would like. Okay, sorry if not enough time. Okay, 6, 5, 4, 3. Okay, sorry if this is sufficient. And I think one student got correct. Oh, sorry. So, okay. Okay, one more. This should be a short question. Okay, one more. Yeah, but it's upside down. Okay, I think should be true. Should be true. Remember the unique property on if you separate integration based on each grouping of 4 variables. Okay, so I think that's all for today. Let's see who is the winner. Oh, okay. Congratulations. Okay. Okay, so that's all for today's class, and see you next Monday. Okay, and if you haven't scanned the QR code, here's the QR code. Okay. And if you want to discuss, like maybe you have any suggestions for your online course, okay, let me know. Okay. Open for any discussion. Okay, if there's no questions, you can leave the meetings and see you on Monday. Okay, thank you all. Thank you for joining the course.
Professors, so far that the tentative date for the final exam, it should be the second week of June, right before 10th.
Yeah, it should be. Yeah, my estimations for schedule.
Okay, thank you, professors. And like so the platform for the final exam, right, is going to be quizzes.
Yeah,
And
probably, or maybe another platform, but that has similar feature with quizzes.
okay, professors. And like I wonder, since like you already mentioned that you may reduce the weight percentage of
Yeah, yeah,
the quiz,
yeah.
right? So the weight of the final exam would increase, right? Or
Probably the weight for the midterm will be increased because
oh,
it's
because
the paper
the
based.
final is exam. Oh, okay.
Yeah,
Oh, okay.
I will increase the percentage for the paper based and reduce a little bit for the online one.
Oh, okay. Thank you,
Yeah.
professors.
Okay. Later on, I will tell you about the percentage. Okay. Okay.
Oh,
Thank you,
okay.
everyone.
Thank you.
Yeah.
Thank you. Appreciate that.
Okay. Thank you, Paulis.